My name is Nicole Brown. I'm a research engineer in the ISYE department. I'm Industrial and Systems Engineering, those of you who are always on this side of campus. I work under the direction of Dr. Eva Lee. She's a professor in the ISYE department, and she's also the director for the Center for Healthcare Organization Transformation under the ISYE department. It's an NSF center that spans several different schools. She's also the director of the Center for Operations Research in Medicine and Healthcare. Her educational background is that she got her Ph.D. in computational and applied mathematics from Rice. And ever since then, she's been doing absolutely amazing research that has to do with bridging the gap between industrial engineering and real applications in healthcare and medicine. Her research usually focuses on systems modeling, software development for medicine and healthcare, medical decision making, which you guys are going to hear some about today. It's a really exciting presentation. She does work with hospitals, public health organizations like the CDC, the Veterans Administration, pretty much anything you can think of that has to do with healthcare. She's had a finger in it or a hand in it or a whole self in it at some point. She's a very passionate researcher. She's up pretty much all hours of the night doing research, but she's also a devoted mentor. I'm happy to have been under her tutelage as one of her graduate students. And today's talk is going to be about a machine learning framework for medical decision making, and it's really exciting, so I hope you guys enjoy it.
Thank you. So thank you for coming to this talk early in the morning, and also thank you for the opportunity for me to present the talk to the IBB community. So just some of the history. Nicole already mentioned that, so we started some of this research really back in 1998 when I first came to Georgia Tech, and we were very fortunate to receive the National Science Foundation Award as well as the Whitaker Foundation Award that helped to establish the Center of Operations Research in Medicine and Healthcare. And that's really the first of its kind in ISYE in terms of really using systems approach to look at medicine and healthcare. So many of you may already know that ISYE has a history of doing healthcare research, but most of it is really on healthcare management and really graduating master students and working in hospital as managers and doing day-to-day operations. But so this program really focuses on research advances in biomedicine. And so we are very fortunate because a lot of the key players, we work with the top medical schools and on a lot of the research. And the center really focused on quite a bit of work based on health risk prediction, early disease diagnosis, and how do you design optimal treatment plan for different type of disease, drug delivery treatment outcome, and also quality safety, and also public health and global and also policy analysis. So as you can see, the reason why it is so broad partly is because a lot of the problems can be looked at in a systems view, and there are many methods that one can apply to it. So then the second center, actually, we just got it several years ago. This is the NSF Industrial University Collaborative Partnership Center. And basically, we were partnered with the only rural public health program in the country, which is at Texas A&M. So that's the two of us actually submitted the proposal to PIs. And NSF actually really loved this because that's the first center that focused on healthcare. As you notice, a lot of the work in the previous slide that we mentioned are dealing with patients, dealing with the biomedicine and the science, basic science part. This is really application and delivery side. That means if you have advances, how do you actually put it into the hospital, which is actually quite difficult and a lot of challenges. And I think we are also very fortunate to be supported by the health system leaders, and they sign on as the members, and they actually help us to actually implement a lot of this work. So a lot of the methods that I'm going to talk about or use are the decision support system, systems, modeling, operations research, information technology, distributed computing, and also really advanced communication technologies. All of these are being used and integrated together into like a framework in terms of like assisting the doctors or assisting the managers in the hospital. So many of these techniques, in a sense, that give you a very nice, powerful tools where you can actually model in the cell level, in the molecular level, in the human level, and also really in the facility and system global, like across the nations. So that's the beauty of it and also the fun of it. Of course, the students sometimes would worry about exactly how are they going to focus and what do they have to learn to achieve that. So as you notice, that's why we do need to spend a lot of time with the students because it is important to figure out what can they do and also what what is the interest that they can actually contribute the most. So in a sense that this work comes really at the right time, is that because they're major forces that really make us think about healthcare reform, and also really how do you translate the scientific work into the hospital. So there's a lot of initiative now in NIH, in NSF. So it gives us a lot more ammunition to do the work. And I want to emphasize for those of you, if you have taken ISYU courses, that traditionally ISYU look at logistics. That means they look at scheduling, they look at things that have not much to do with the patients, but more on the operation side. But the work here really focuses on the doctors, the patients, and the healthcare systems. So the basic science part, so we look at diagnosis, we look at treatment design, like cancer, HIV, treatment design. We look at how do you deliver that. Once you get the design, the advanced design and novelty of the design, how do you look at outcome, treatment outcome? How do you predict that patients' response to different treatment and map them up so that when a new patient comes in, you can use those characteristics and be able to guide them to the right treatment? And also public health. And in the delivery side, we look at the quality, the operations efficiency, which is always part of what ISYE is about. Information management. Many of you know, if you're working in the lab, you generate huge amount of data every single day. How do you actually manage those information and use them all together, right? So that's really the key part, is a lot of times we use them just one set at a time, but not all together. The change management, that's about the NSF Center, that's about the health organization transformation. I must mention that it is really an interesting experience in a sense that when I first started this area, I worked in the cancer treatment design. And when we first started 15 years ago at Columbia University in the medical school, the doctors thought that we were crazy when we were thinking about how do you put this in. We want real-time planning in the operating room. They thought it is crazy because first, the problem is too hard to solve in real time. Secondly, even if you do it, they're not going to have the machinery that can accommodate your technique. Okay, so right, that's really the key part. Why do you have to change them? Because they do need to change the configuration in the operating room to allow you to actually implement those changes. So that's basically the overarching focus. So for this talk, I'm going to talk about machine learning, basically talk about discriminant analysis and predictive model in medicine. And this is one of the hottest topics in the in medicine nowadays, and actually in many different areas. So the outline of my talk, I will talk about a little bit about what discriminant analysis and predictive models are. Just give you a general schema what it is about and the mathematical concept. Now there are many different methods, so you can always apply your favorite methods. Of course, some methods work better than the others, right? So that's the key part. I will show you some of the real applications. Most of these are clinical applications. And then if we have time, we talk about other medical decision making, but I don't think we have enough time because the talk is really quite long already. So what are the challenges? So when we think about systems, so think about the data that is available, not just the biological data you have to analyze. It has the clinical data, it has the historical data, the outcome of other patients. How do you utilize all these data and be able to identify some discriminant patterns from it so that it will help you to advance what you are looking for, right? In this case, there are many ways that you're trying to advance. Maybe you want to predict the health risk of an individual. You want to look at the disease detection, and I will mention one of these disease detection that is quite novel and also really early stage detection. How do you really monitor the treatment and the prognosis of the individual and be able to change the course of the treatment if that is necessary? Knowing what is going on and be able to change that. What are the therapeutic choices? And how do you perform public health intervention and the population health? So public health intervention here, a lot of times we separate them with medicine in a sense that that's the part that a lot of times there's even like school of medicine, there's school of public health. But if you think about how do you decide when an individual should take a vaccine? So that's a very important question. Who is going to answer that question? Is it the doctor, the scientist in it, or is it public health leaders where they have to say, okay, we are going to start this vaccination and this is the policy we're going to adopt. So those are all intertwined, and I will give you one of the example where we are looking at that. And we got very good results. So a lot of times if you look at the outside world, like what do they call this area is medical informatics or health informatics. And I mentioned about biocomputing. So everything we're going to do with data, you will have to implement some very powerful tools so that you can actually solve your model. So that always come hand to hand. So health informatics really deal with the organization and optimal use of biological and medical information, data and knowledge related to all type of disease and clinical conditions. So you notice what I mentioned, right? I have information, I have data, and I have knowledge. They can come from many different forms, and I would like to use them in the most effective way so that I can get some information. So the idea is that I would like this process to be able to facilitate discoveries, new discoveries and interpretations, so that we know from this data that will help us in the development or evaluation of innovative technology for early detection, intervention, diagnosis, drug delivery, optimal treatment design, outcome prediction, and population health. So what is discriminant analysis? This is one way to look at things, is that if I had n groups of different things, I would like to be able to classify an entity into one of these groups. So that's the idea. So if you think a very simple idea, for example, if you go in to see the doctor and you complain about you have a chest pain, so what the doctor has to figure out is, what are you, like, okay, you're not having any disease, or if you have any disease, what type of disease you have, right? First of all, the first step is that two step, normal versus not normal, right? So that's like, if you're normal, or your chest pain could just be maybe you bump yourself or something happened that is not important or not of significance that they have to worry about. Or if you have chest pain, they say, okay, this is not normal, so we have to look into it, what's going on. So that's the two groups. But that's very broad. If the doctor only knows that it is not normal, it's not going to help him or you, because he will not be able to take the action of what to do, right? So then you know right away. So that's the disease diagnosis, right? So you go to the doctor, that's what. So we use the training set, and we'll use training set so that it will help you to develop what we call the discriminant rule or the predictive rule. So you use a small set of these and establish the rule. And the key part is the third part, is that when a new entity comes in, you want to be able to classify it correctly. Okay, so all these diagnoses is that they are the evidence learned from the old days that they're going to be able to classify it because that is how the rule works. So an example is pap smear. They take the pap smear test and they diagnose, yes, there is cancer or suspicious of cancer in this patient. No, there is none. But do you know what is the percentage of correctness in pap smear? It's between 60 to 70%, right? So sometimes you use those rules even though you have false positive, because you cannot get perfect percentage in terms of the correctness. So how do we use this type of techniques? Machine learning, a lot of times you hear lots of different phrases that's called machine learning, supervised learning, classification, or pattern recognition. So we use it, my earliest work, actually, when I was at Columbia, I started my position in the engineering school, and our first application is really with the Wall Street and with the consumer patterns. So nowadays, this is all populated in Google, in everything in the internet. When you buy something, they say, well, you may want to buy these too, or customers that buy this item also would prefer this item. So this is called customer pattern recognition. Okay, you look at consumers, what do they like, and then you develop the rule, and they actually 90% of times are very correct. Why is that the case? Why is it that the consumer pattern is so accurate, whereas in the medical diagnosis it's not? Take a wild guess.
Sample size?
Yes, you have what? Huge number of people buying, and whether you like to be a subject of the study or not, you are enrolled, right? The moment you click on it. So that is really the key part. So they can refine it, and they can really look at a very broad base and be able to come up with. Of course, it's also a little bit different when you inject biology to it, right? Human, it's very different, even though we are so alike. So there's also the, of course, credit history. So some of my students actually work for those companies, and they apply these techniques for looking at like whether you should let this individual open the account or not, and looking at the chance of default. There's of course, the economics, where you actually predict the stock market and also investment trend, or economics trend. And of course, there's the many different fancy applications. One of my cousins actually work for the FBI, and they look at, they use this type of techniques and look at forensics and picking up the soil, picking up little fiber from the scene and trying to reconstruct all this information. So those you have heard a lot. Now medicine, in a sense that a lot of times the most popular techniques in medicine has always been the p-test and the logistic regression, partly because statistics has always been really readily available to medical research. So the using machine learning techniques has not really been very popular until really the last 5 to 10 years that it gets really, although if you talk to National Library of Medicine, the director has been telling me they have been looking for this type of idea for the last 20 years. But so I think they actively really want very sophisticated techniques. So a lot of these techniques can be used in many different ways. And I listed prediction of disease, early detection and intervention, I already have mentioned. So you can actually also use that in terms of predicting the behavior of individual. When they come into the ED here, emergency department, how do you predict that the outcome of this individual and who will be readmitted, which is one of the very big problem or big challenge in terms of for the emergency department. So some of the techniques that I'm going to mention today involves the combinatorial pattern recognition, artificial intelligence, and support vector machines. So the favorite methods or the well-known methods, statistical analysis, data mining, are the a lot of times have been used a lot, and there are bottlenecks in those approaches is that many of you know that statistical approaches a lot of times have trouble with a huge amount of data. The dimension, the curse of dimension is difficult to manage, and you have to have a really huge sample size, which you don't have that luxuries in many of the clinical trials or any of the clinical study. And neural network is one of the easiest and most friendly approach in terms of heuristic approach, where you can write a very short algorithms and you can find some solutions. It's not exact approach, but it gives you a very fast solution. So what is the general schema? So no matter what method you're going to use, the schema is identical. So first, you're going to identify the attributes or the patterns for a given data set, any data set that you look at. Then you develop the mathematical models and the computational engine so that you can actually establish or learn and establish that predictive rule. That is the first step. Then the step 3 is that you validate this predictive rule to see how much confidence you have in that. And of course you refine, you retrain. Here you can see you have new data, you come in, you refine the rule. And the most important step, if you indeed want your rule to be used at all. So if you don't, then you can stop at step 3 or step 4 and you can write papers, and these will be the classic papers that you will see a lot of times. But if you really want to figure out, are there any clinical significance? Can I actually translate my work into the clinical setting? Then the step 5 is most important, because that is the time when you really want to know, can you really predict? Okay, so because you can validate really well, but you cannot predict, then that means it cannot be translating to the usage, the actual usage. So how do you identify attributes? So let's take a look at it. So I do not know the background of the audience, so I'm going to give this, some of you, could be really simple, the next few slides, and some of you may be new to you. So I'm going to start with the idea of what attributes means, okay? So just to build up your concept of what attributes. For example, I have 3 types of plants, iris plants, and I have 50 in each of these. What I can measure is the attributes, or I can mention attributes as the measurement of the sepal length and the sepal width, and the petal length and the petal width. Okay, that could be part of the attribute. Is it easy to obtain these attributes? The answer is yes. It's usually a lot of times you want the attributes to be really easy. So the output is that I want to know, if I pick an iris plant, I want to know which one it comes from. Okay, so is that easy to understand? So you have 3 groups, and you have 4 attributes. So if you look at how you register that, then you can register, you can register like this one, is that you have the attributes here, and then you have the class of what this iris belongs to. So that's the 3 groups with 4 attributes and the class. Then now we match, so that's the plant. Now for those of you, if you enjoy wine, is that you, of course, there are some very good wine tester that they could taste that could actually tell you exactly where the wine comes from. But of course, you can also do some little scientific tests is that you can take the measurements of these constituents in the wine, and in this case, we have 13 of them. And again, we have 3 cultivars, and now you see the sample size we change, so we have different sample size in each of these groups. And so now in this, again, it's numeric attributes. I have 13 of these attributes, and then I know each of these sample, which group they belong to. So that's how you represent the group. Now let's march into human. Okay, so we are a little bit more complicated. You don't just measure our height, or of course you can measure that too, but there could be different things. So thyroid disease. So this one, we have like different ones, 3 groups, normal, hypo, and hyper. And then we have different measurements here. So now, again, you notice that, what are these measurements in your mind if we look at medical stuff? It could be biological data, it could be clinical data, it could be laboratory data, it could be images, right? It could be anything. So if you look at the next one, so now we march into the real data that we're looking at. So this one relates to Alzheimer's disease study, the MRI images. This is a study with on biomarkers and metabolomics. And this one is a microangiographic images. And the patterns here, and I must note, the patterns here is looking at the branching and how many branches are there, these vascular capillaries, and where they are located. So this one we actually look at metastasis of the cancer across the body, as well as different type of disease, for example, premature aging and macular degeneracy. So you notice the patterns becomes really difficult, right? Now you don't just, okay, I count it or measure it. Now you have to come up with an algorithms to just look at the patterns and figure out what they are. So once you have the attributes, and this may be just given to you, then you have to develop mathematical models and try to solve them to establish that. So what is classification? In the very simple sense is that, for example, I have 2 groups here represented by the little color. So I can put the hyperplane, so just a straight line here, and separate the 2 groups. What do you notice immediately? First of all, did I do a good job in the separation? Yes or no, right? I mean, I do not know if I can actually separate these with a straight line. The answer is, if you stare at it, no, we cannot really separate it with a straight line, right? So the objective is you can minimize the deviation, minimize the maximum deviation, the margin, and all this, but we do have errors, right? You see right away. Misclassification may not be possible to avoid, and we just have to make sure that we can do the best we can. So how do we go about doing that? So the concept, and I'm going to mention to you, like, how can we actually classify? So forced discriminant rules means that if I have n groups, I'm going to put an entity into one of the n groups and nothing else. So this one works well. Like the previous example, what you see then is that I have 2 groups, right? All these dots have to be either in one or the other side. So it works well if the groups are separable. That means it's easy to separate them, and then you don't have a lot of errors. Otherwise, you will have a high rate of misclassification. The next one is that because of that, let's say we don't classify them all into one of the n groups. For example, look at the thyroid disease. So I have normal, hyper, and hypo. So the patient comes in to the doctor discovered that, okay, the thyroid gland is not normal. Okay, so he said normal versus not normal. That is what? 2 groups, right? So the chance of error may not be so high, but can you take the course of treatment if I tell you the patient has abnormal thyroid? No, because the course of treatment is what? Hypo and hyper are totally opposite, right? So in this case, this is exactly what we're doing, is that we lump those subgroups together. So in this case, you reduce the chance of misclassification, but it doesn't really help you in terms of like trying to take the next step. So that's the trade-offs. So what are we doing? This is one of the focus in my lab, and we're looking at, in this one, I project the 3 groups here, represented by the 1, 2, and 3. So I just project it into the R2 plane. So you notice that I have, this is what the separation is, and you have some errors that you can see. So this is what we call the reserve judgment. So we, instead of classifying it only into n groups, like in this case 3, we are going to make a reserve judgment here for those that are fussy. So this could be the case that when patients come in, we have some test and we figure out, okay, it is not in this group, or the other group, but we really do not know exactly where the patient is, but we don't want to misdiagnose it. Then you put them into that reserve judgment. What it means is that you will take other measurements to separate them and to avoid the misclassification. This is the key. A lot of times in medicine is a little bit different, is that classification means that you are going to make the next step, right, the treatment or anything. So you really don't want to treat the patients wrong, and you would like to be really taking a very careful step in order to be able to have the correct diagnosis. So the advances that we have, first we developed a viable computational model for multi-group classification. That means it depends, it doesn't matter how many groups you have. For example, I could have 8 different types of skin disease that I need to figure out. So you can apply this model. You can apply this model for cancer patients. Yes, it has cancer, or no, it doesn't have cancer. So we analyze the complexity of this model and identify the characteristics of the solution space. So of course, the most important part is that we want to test and validate the ability of such model and how it classified different type of applications. And we also want to really incorporate the predictive rule for clinical decision making. So that's really key part. Now you notice I put in parentheses the NP complete and the theory and computation here. So for those of you, if you are from computer science, NP complete, you know that's the class of problems that are the hardest in terms of computational effort. And these problems fall into right there. So that means there exists no easy way to solve the problem. So it is a very difficult problem. So in general, here's what the problem can be stated. You are given G groups with n entities, and each of these entities has m attributes. Now I'm going to have just one slide that has all the mathematics to it. So the mathematical model basically assigns a variable to each of the entity. That means if it is individual, a human, so we assign a variable 0, 1 to this individual. And 1 means if it is classified correctly, 0 means it doesn't classify correctly. And then there's a mathematical expression to describe which group it belongs to, and also mathematical expression to describe that it is being placed in the research judgment, and a constraint to really constrain the percentage of misclassification in each group. So the objective is really easy, is to maximize the number of correct classification, right? So like I say, it does not matter what model you're going to use. All that you are going to care for is the best results coming out from the mathematics. So the outcome then is a predictive rule represented by a mathematical expression. In the case, you can think of it like a regression line. You know, it is a curve, like you know how you fit all the points. But that line fitting is not sufficient, because the most important thing is when you have another entity, you want to be able to predict using that particular fitting line, right? So that's important. So the outcome from our model is not a line or a curve. It's actually a transformation. It's a mathematical setup. And that's probably the most complex part in terms of explaining it to a lot of the doctors, although sometimes they really don't care because it is just a black box in the back end, right? It's not like we're going to test them. So like I said, this is the only mathematics that I'm going to include. So this one is the entity J from group G being classified back in group G. Okay, so that's the symbol U, GGJ. It's either 0 or 1. If it is 1, it means it is classified correctly, right? Because I classify the J entity from group G back into group G. And I want to maximize that. So I sum it over all the groups, and I sum it over all the entities. So this is the mathematical expression. I won't go into detail. And this one is so we want to maximize the total correct classification, and we want to constrain the misclassification, and in this case I put 15% in it. So you can put any favorite number that you want. So the key why this is so important is that a lot of times if you do not include the misclassification constraint, you may come back with a solution very fast, but they are really bad solution. It may only, like in one of the cases, some of the heart disease one that we looked at, some of the models actually come back with only 40% of correct classification. So it is worse than a blind mouse, right? If it's blind mouse, yes or no. So at least you get half and half. So you need to be able to have those property. Although it is not true that all models can have that. And we actually, this one came up with a very good solution. So what are the characteristics? Like now if you are doing computer science or systems, engineering, a lot of the work, in addition to the application, there's also the theory and the computational side. So this is basically some of the computational area that you can look at. This is really the first efficient computational model for N groups. Okay, so that's, if you look at the literature, a lot of times is they use the set of data and then they define the model. So if the data only has 2 groups, you define a model that has 2 groups. So we actually start out with the model and you can apply it to any number of groups. It has a nonlinear transformation that manages the curse of dimensionality. That means you can have 1 million attributes, but it will be transformed into the space where the number of groups are. So this is the most powerful. A lot of doctors love to know exactly how this is done because this is exactly why it is so powerful and it overcomes a lot of the statistical issues. So it allows constraint on the misclassification rates. It provides a reserve judgment, which is really quite important in many different settings. And it also allows you to develop predictive rule at different levels. So I will show you that. So in theory, like for those of you interested in computer science and systems, so I mentioned this is NP complete. It also is very interesting. This is one of the very few models in machine learning where it is universally strongly consistent. That means no matter what percentage and what distribution you have in your data, it will always converge to the optimal solution. So this is a very beautiful theory to have in terms of in your solution space. And it also, in a sense that I should mention, the key part here is the following, is that it really works well when the sample size is very disproportional. That means I could have the normal set or normal control set to be like 100 patients, and I have the disease set only 10 patients. Okay, so in many cases, it's that they will bias towards the sample size that is big, but in this model, it actually overcomes that very beautifully. It is still very difficult to understand all the characteristics, so this is just some of the work that we do in terms of the theoretical part, so I will skip them. So how do you validate the predictive rule? Now, you have the data, you get the attributes, you ran it through the mathematical models. So the next thing you want to know, how accurate is it using this particular predictive rule. So basically is that you are applying new entity to it, and like I say, the key part is that the predictive rule, establishing it is very hard. That means it takes a lot of computational time. It could take months of CPU time, and I have 176 computers CPU with me, and at any given time it is running lots of jobs, and lots of jobs that relates to medical decision making and machine learning. So getting the predictive rule is hard, but really testing it, if I have a new patient, I take the measurements, it will take nanoseconds. It's very rapid. So how do you validate such a rule? So tenfold cross-validation is a common way, is that you use your training set, you partition it into 10 almost equal partitions. You use 9 of them for training. That gives you a rule, and then you test the one-fold, and then you repeat 10 times. So these give you an unbiased estimate of the predictive correctness based on your training set. And this is where everyone does, and you can do also leave one out or many k-fold. It doesn't have to be 10-fold. So the next step is retraining. So it's easier to show you in the figure here. So I have experimental data, I have clinical data. It comes in. There's the pattern recognition module where I mentioned is that it could be different type of data, and if it is imaging, you have to come up with the algorithms to figure out all these. And then there's the feature selection. For example, if you actually come up with 1 million type of attributes here, so each individual has 1 million type of attributes. So you go through this feature selection, it may select say 5. It learns and get the classification rule for you. It goes back here and continue to train until the solution is satisfied. Okay, until you say, yes, this is the correct classification rate that I accept. A lot of times, over 75% is already the best result, or sometimes we are very lucky we got 95%, which is really very good. And then the solution will be represented out here. Many different groups. And then the reserve judgment, what do we do? From the reserve judgment, we continue like here and start classifying again. So you select different type of attributes. So this is the beauty, is that in order for us not to misclassify, we have the reserve judgment that allows you to continue to do the multi-stage classification. And this works really well in terms of in the medical arena. Blind test. So now, as I mentioned, blind test is really simple. You just take a new entity or patient, you take the measurements that where those patterns form the discriminant rules, and then you test it. So I want to mention something very important. Prediction is not the same as correlation. Okay, so if A then B, that is a correlation. So that's what you look at the phenomena. This is if I do the experiment, I see this result. That's the correlation, and you find correlation. So prediction really completes the loop. That means we have A is equivalent to B, or A implies B, and the conditions of B are sufficient to really describe A or predict A. Okay, so this is really the power. A lot of the work now looking at characteristics of things really focus on the correlation. Okay, so, and that's why I'm saying is that prediction or predictive medicine is still rather new in the area, because a lot of times, because the traditional way of thinking always look at correlation without the predictive power. So we tend to really overfeed the logistic lines, right, the regression lines, because we are thinking we want to look at all the characteristics without really thinking, well, if you have a new patient, how are you going to predict using that particular rule? So it's very different thinking. So now I won't be able to go through all of this. Absolutely not possible, but I'm going to show you some of these that are really exciting results. And the first two, I think we can go through in great detail. And the first one really is a very important work, and that really touch upon the medicine and public health. That's why I want to mention that. And then second one is on early diagnosis of cancer. And then we have the Alzheimer's disease project, and then we have the also metabolomics project. The last two is different. As you notice that the last two, actually the fifth one is really trying to look at what are the characteristics that we can predict how patients go to the emergency department. It's very interesting. We were able to look at 35 pediatric sites and be able to predict what are the discriminant patterns inside all these characteristics that can predict that, yes, this place will be visited by lots of children at a certain time. So it's very interesting, the characteristics. And these are like help them with the policy and with the operations. And the last one is predicting the readmission of patients. Also very interesting, because Children's Healthcare of Atlanta actually was able to capture all the information, not only the patient, but also the utilization and the nurse, what they're doing, the doctors, what they're doing, every single minute during in the ED. So we were able to predict. So those are quite interesting things. Like I said, I just show them out here so that you get a sense. Like if you're not so inclined to bio stuff, then you can look at the more healthcare delivery side and still can use this type of approaches. So let's look at the predicting the immunity of vaccines. So the study really is to develop methodologies to predict the immunity of vaccine without exposing individuals to infection. So that's really to address a long-standing challenge in developing vaccines, where we can only determine immunity or effectiveness long after the vaccination, or often when the individual is being exposed to the infection. The study actually was supported by the biodefense work from NIAID. Is really trying to figure out how do you actually develop evaluations of vaccine technology so that we can actually tell the individuals if they should take a certain vaccine or not during emergency or during pandemic. So two different models have already been completed in our study. So the first one employed the yellow fever as a model system, and partly because yellow fever has been administered to nearly 500 million people over the last 70 years. And a single shot really induces immunity in many people for nearly 30 years. So that is a very powerful vaccine, and of course we are not using that in the United States. But describe the great success of yellow fever vaccine. Very little has been known about the immunological mechanism that makes it effective. So basically the design of this experiment is that we vaccinate a set of healthy individuals with the yellow fever vaccine and study the T cells and antibody responses in the blood. And basically the blood is being taken at different intervals at day 0, day 3, day 5, day 7, all the way to day 60. So we got lots of gene expression patterns in the red blood cells for a period of time, over 2 months. And then among that, we have about 50,000 gene time signatures. So now remember, we have, of course, about 25,000 genes in the human body, but these are gene time signatures. That means it is the gene and the characteristic of the gene at a certain time. So there's a timestamp that relates to that. So just to show you some of these, it's like you can see the different dates and how the T cells actually respond. And of course, you know, if you look at these, just look at the experiment, you know there are differences between different patients, but we want to know, are the patients respond well with this vaccine or do they not respond well? Okay, so that's the key part of it. So the first goal is to identify distinct gene signatures that can predict the magnitude of T cell response and the antibody response induced by the vaccine. So we want to know whether there are signatures, early signatures of innate immune activity that could predict the subsequent T cells response. So that's very important because that's how the individual actually responds to the mechanism of responding to vaccination. And how about prediction on the B cell antibody response? So we want both T cells as well as the antibody. The second one is the real one. So first, we want to identify the discriminant patterns. And secondly, we really want to be able to test, are these patterns that we identify that actually could be used for prediction? So we actually validate the findings on a separate set of healthy individuals that received the vaccine, and we will predict, and then we will tell the clinicians and the biologists to tell them, this is what we have seen in terms of the response, and they validate it in the lab setting. Okay, so that's a very easy way to understand that. So a very exciting result. We were able to identify very distinct gene signatures that discriminate the level of T cell response and also antibody response induced by the vaccine. And the blind prediction yields 90% correct classification. Now, this is the big deal. And I mentioned it is really the specificity as well as the sensitivity. So it is both of them. So it is important that we correct classified it, and also it doesn't have a high false positive, right? So we need both of them, and both of these are over 90%. So this is the first study of its kind, and it really gives us the ability to look at the design, evaluation, and also really looking at how do we determine the effectiveness of vaccine. And this is still a very unknown problem among in this country. For example, it is difficult to rally the citizen to take the flu vaccine because some of them worried about side effects and they simply do not want to come. So now you can just rub a little bit of the DNA and say, okay, this is the few gene signatures that we have to look at, and then we will be able to process and know would they respond well or not. So these are the rules, and I know it is not, so these are the genes at different dates that we identify. These are the rules. That means that these are the ones that use only 3 of these, and you see out of all these 50,000 gene signatures, we select really between 3 to 5 of these gene signatures that are critical. So you can think of it, if you look at it in a systems viewpoint, then you can look at a system where you have the big nodes and they are connected. These are very big, and you have thousands or 50,000 of the other nodes are tiny little ones that are not so important. If I pull the connectivity of these big nodes, what happened? The system collapsed, right? So these are the critical nodes. So these are the critical signatures that allow us to predict. And basically, each of these columns correspond to a rule. Why is this important? Is that, in a sense, you can think of it, it's like a policy. If we test things, it is nice to have different options for you to test. Now, this is, in a sense, is interesting. A lot of times we look for just one rule, but the biologists really like that it has many rules. So what are the clinical significance? The ability to successfully predict the immunity and effectiveness of vaccines with facilitate the rapid evaluation and design of the vaccine for new and emerging biological agents. So that's why I mentioned the work was started actually from the Biodefense Fund, when there is a great sense of urgency to be able to understand what type of biological agent that we are facing and how fast can we come up with effective vaccine. So this really identified the individuals who are unlikely to be protected by the vaccine, and they should be exempted from really taking the vaccine. And also it answered a very fundamental questions that could lead to better vaccinations and prevention of disease. So we have a paper of this published in Nature Immunology. What is next? This one, okay, good. So we just finished the study, the last, I think maybe 3 months ago. And this one, as you notice, the first model is yellow fever, and the second model actually took 3 years in terms of getting the sample data points. So just to give you an idea how long it could take, right, in terms of using human data. So there are 3 trials of patients, 2008, 2009, and 2010. It consists of different flu vaccines as well as flu myths. So some of them is just spray in the nose, and some of it is a vaccination. So we are able to also predict 90% accuracy across the trials. So basically the idea is that we use one trial to develop the predictive rule, and then we predict the other 2 trials. Now you notice this is really fascinating, is that it is an expensive study in a sense that it involves human subjects. It involves a lot of blood sample measurements and a lot of genomic studies. But it also takes time to collect all this, right? As you notice, this paper, at least we spend so much time in just collecting the data. But the results really is very exciting, and is also published in Nature Immunology just last month. So the next step is that we really are looking at flu vaccine, and actually many different types of vaccine designed and for infectious disease outbreak. And basically, if you look at just flu, don't even look at the very fancy biological agents. Just look at flu vaccine. It takes a long time to develop the right vaccine, right? You have to test it. And so the idea that we can actually, after 3 days of injection, we were able to predict if it is actually working or not, would really speed up the design of the effective vaccine. So this is really the key part of the study. So the next one, so you notice now, this one, as I mentioned, it is biomedicine and it is public health also, right? Because vaccination itself gets into the public health part, where the CDC is asking citizens to go to a certain place, and that's like will help them in terms of determining who should get the vaccine. And this also has a very, very great impact to protecting the military personnel, because many times they are exposed to different type of agents, and a lot of times they will be asked to take vaccination, and it could have grave consequence. And if we can predict that, yes, this individual should take it and this individual should not, because he or she may suffer from adverse reaction, this is really important. Even though it is 90% correct, but you know, when it comes to medicine, it's difficult. If somebody tells you it's 100%, you're going to start wondering exactly what that means. Right? So the next one, and I don't think I have a lot of time, but I would mention this one because this is kind of a very futuristic type of work, but it's really, now everybody is really excited about that. And we started this research about 7 years ago. So we looked at epigenetics and looking at the sequence signature to see if we can actually predict certain phenomena. So CpG islands are the region of DNA sequence with high concentration of CpG dinucleotides. So it's about 6 to 12% versus the normal 3%. And across the human, we have about like 29,000 CpG islands. So why are they important in epigenetics? If you look at the methylation status, is that this is the normal cells, this is the island, and this is the schematic description of methylation and how it looks. In the cancer cells is that it usually have the hypermethylation followed by hypomethylation of the gene body and the bulk chromatin. So it gives a very specific information when it comes to cancer cells. And aberrant methylation of normally methylated CpG islands occur frequently in human cancer. And the aberrant methylation leads to inappropriate gene silencing, and a lot of these genes are responsible, for example, in some cases responsible for cell deaths. If the genes are silenced, the cells will not die, and that is the landmark for cell growth, proliferation, and also the marching into the cancer formation. So what we are looking at is epigenetics phenomena and the silencing associated with aberrant methylation of promoter region of CpG islands. And what we want to know is that are there any gene signatures or are there any sequence signatures that will allow us to predict such phenomena? So that is the most, now this is no longer about the gene that is responsible for cancer, like the BRCA1 gene or those genes, but we are looking at the sequence signature. That means that little segments of the genes that in your body that would give you some idea, will you actually be more prone to have cancer or not? Okay, so very little is known about these genes, why they succumb to this aberrant event. But what is known, and this is the really interesting part, is that these are the genes, and these are the location of the chromosome of these genes, and these are tumor type, and these are the genes that are silenced by methylation. Okay, so that is the inactivation of the gene, and you notice that it's a broad variety of genes being silenced, and it covers a huge amount of cancer type, right? So that is the interest part that we would like to look at. So we want to understand the importance of CpG island methylation in cancer at the genomic level. So we want to be able to develop predictive rules so that we can actually identify some signatures that could predict the methylation status. So the idea is really to be able to reactivate the genes being silenced by reversing the DNA methylation. So you notice this gives you a new therapeutic sites, right? If you can identify those sites, you can actually target at those sites and reverse that reaction. You can develop novel treatment strategies aimed at blocking or reversing such methylation status, and also develop methylation markers for cancer prediction, treatment, and prognosis. So that's really the broad scheme of it. And it's really interesting because I have to say, as you notice, my training is mathematics, right? It's exactly the opposite of biologists in terms of knowing anything biological. We only know everything as equations. So, but on the other hand, this one actually is quite beautiful because this one we started quite a long time ago, and that we actually identified some of the signatures that actually was known by the biologists. Of course, it came out from our computer. So first, the biological data is that we analyzed the susceptibility of 1749 unselected CpG islands to de novo methylation driven by the overexpression of DNMT1, and then we identified features and developed classification rules. Then we employ these CpG islands that are given to us by the cancer biologist and develop the rule, and then classified it, and then try to determine the correctness of that. Then we also classify the ones that are unknown, and then do a prediction on the human chromosome. So this is the general schema. Very simple to understand and very complicated to actually achieve it. I said this is the methylated CpG islands. These are from the breast cancer cell line. This is the unmethylated CpG islands. So that's the pattern recognition. Oops. Okay. This is the first step is that you have to just the input is really all the sequences. So the first step is pattern recognition. So you run through the computer program that we have developed, and it comes back with 20 million little sequence of patterns. Okay, how long does it take? The answer is very long, because this is a very difficult problem in terms of just looking at short sequences. So we look at 5 to 12 base pair, and once we get the sequence and the patterns, then we select out of these patterns a small subset, and then we classify it. And then we classify them into different groups, whether it's methylated or not unmethylated, and then we apply the new one to it. Okay, so that's a general schema. What do we get? In the training sets, we got 90% correct classification, which is really quite exciting because that's the first time where it actually identifies sequence signature that allowed prediction of methylated versus unmethylated sequences. And then in the blind prediction, we were fortunate to have 44 sequences, and we were able to we achieved over 80% correct classification on the two groups. So now you notice that it's quite interesting is that out of the 20 million, we select only 7. So here is the key part you will always remember, and especially for those of you that are very familiar with biological work and the wet lab, is that you always generate huge amount of data. How are you going to be sensibly really nail it down and get very few of them. That is the key, okay? Because you can have a million of them and then you overtrain. Okay, so you must have a very small set, and these are the key ones. So 2 of the patterns out of the 7 identified by our algorithms actually are known entities, the ancient retroviral elements. So we were able to pinpoint exactly where they relate to cancer, exactly which chromosome, which location, and where it has that particular pattern. So it is very interesting because it opens up some idea of how do you actually intervene in the therapeutic level. The results very exciting, and the interesting part, so we actually published the results in PNAS, and within 2 months, I believe if I didn't forget exactly which group, I think it's the Duke group, they were able to reproduce the result using the mouse model. So now when somebody told you those little signatures, then you can apply it right away, right? It is very hard to find those signatures to begin with. Once you have them, it's easy to test it. So what did we do is that we actually applied it to the chromosome 21 and 22. So if I mention at the beginning about how many of these CPG islands that we know in human is about 29,000, but for the last 20 years, using biological approach, really less than or fewer than 2,000 has been analyzed because it is really quite expensive to analyze this, and you don't know which one to analyze first, right? So what we do is that we actually applied our predictive rule to chromosome 21 and 22, and we identify out of that, I think it's about 1,500 of CPG islands, and out of that we identified fewer than 60 of them that is methylated prone, and then send it back to the biologist to test it in the lab. So now, in a sense, it really helps the experiments because now you actually prioritize what CPG islands are more interested to analyze first, right? So they actually went and analyze this, and we were able to yield 85% correct. The odd thing is that we started out with the breast cell line, and we are predicting the lung cancer. So this is the strange part. From my point of view, I have no understanding about the difference or the similarities, but what you do notice, if you remember the slide that I put all the cancer cells, there's clearly a lot of information about the cells and about the cancer of different types and the methylation and epigenetics. But what most of the groups have been doing is that they have been focusing on one type of cancer at a time, right? This is the focus of the work. So we're able to really just spread it across. So basically for the chromosome 21 and 22, it gives us really good results. So we have the paper in cancer research, and then the full analysis now is we are looking at, now we march right into the lung cancer cells, and then we look at the patterns, and for this particular study we were able to select 15 of the discriminant patterns out of over 2 million of those that we identified. So really the key part is about how do you actually design experiments in this case. And this is the same as if you actually design drugs. Where do you find the binding site? And a lot of times you have a clue, maybe 15 of them works really well, or 15 of them you want to test. How do you identify the ones that works better? And go for that first, and that's very important. So the broad impact, this is really the key part. It really opens up the opportunity to identify methylated status of all CPG islands from the human chromosome, and it takes us really no time. So to test the 21 and 22 and come back with the prediction take us only 7 days, and that's 1,500 CPG islands, right? So you notice that the 1750 that were being identified earlier, that takes more than 20 years of work because you have to do it experimental. Now we can actually really rapidly check that very fast. So in the global aspect is that we can analyze it across many different types of cancer. And as you notice that there is a lot of correlation between different types of cancer, like between prostate cancer and breast cancer and all the others. So this is really an intervention, early intervention and novel treatment idea because it opens up the molecular target for therapeutic intervention. So this one, I only show you a few pictures. So this one, we have lots of patients. This actually was the first study that I have ever wanted to do when I first started machine learning and prediction. when I started at Columbia and building this model, I really wanted to do Alzheimer's disease. But at that time, when I asked them for patients, and they told me, Eva, we have no patients, and we only will know that definitively they have Alzheimer's disease until they died, and we do an autopsy. Okay, so that's the 15 years ago. So, and maybe it was good because then it gave me really a few years of time to develop the models, to really understand it really well, applied it to the all the customer and consumer market and all the things in finance, and then come back to the medical part. Now we have lots of patients. Interesting thing, what do we get in this case is that we have the mini mental health status exam. We have the different type of you ask them to use different things. You ask them to draw the clock. You ask them about the depression scale, and ask them about words that they are familiar with and what is their favorite. So this is what we call the neuropsychological test. Very simple test, but a lot of times, as you notice, this test has many different components, and it is difficult to actually figure out what can we use it for in terms of diagnosis. So we are the first group actually use it and just finished the study, is that these are 3 group of patients that have the normal brain, and then the one with the early cognitive impairment, and the one with Alzheimer's disease. But when we were given the information, we were given the neuropsychological data, the MRI imaging, as well as many other different information. And interesting enough, it's only 2 groups. So the doctor told us one is the normal patient control group, one is patients with Alzheimer's disease. And we find 3 groups. So we actually find out one group that has early sign of cognitive impairment. So that will be the group that will allow you for early stage intervention. Okay, so that's in a sense that it really gives you the capability of slow down the progression towards Alzheimer's disease, or even stop it, because there are medicine that we can actually provide to the patients. So this is very exciting work, and we finished the work, and I'm finishing up the paper on this one. And the predictive rule is the first set of patients is 100%. And that really shocked me. Of course, I go back and say, all right, that is not possible. And so we look at another set of patients, and now we have about 2,000 patients from also multi-center with data collecting. So now we refine it, and it is about 90 to 95%, which is more comforting, because it really is difficult to say you have a predictive rule that is 100%, because there has to be some, differences in human. For example, I'm a good example is everything that the doctor measure me always tell me I'm different than everyone else, right? So you would need some exception there. This is about metabolomics, and just to show you, this is about patients. A kind of interesting biomarker study in Dean Jones' group is that they have patients coming in and they measure the metabolites, and we take measurements of these and be able to predict the different level of metabolomics that is in the body. And this is actually very important for some of the sports medicine study. As you notice in the newspaper, a lot of times when the young individuals collapse on the court and have heart attack, usually that is always the first sign, and that is also the last sign, because they usually died. So in some of the sports medicine that we do, we take metabolites of the individual and try to track them. Not so much about tracking drug or anything, but really tracking, are there any really simple little changes in these metabolites that will give us a hint of disease or deficiency on certain levels, so that we can actually intervene right away. So these are, like I said, these patients are actually healthy patients, and they came in the lab, and then they were being measured and all this. So I want to acknowledge my collaborators, and many of them, I don't think I can list all of them. We have been very fortunate. We get fundings from the National Science Foundation, from the several grants from the National Institutes of Health, and also from the Georgia SID grants. And thank you for your attention. And if you like to receive some of the papers, or if you are interested in more of these projects, so you are welcome to send me email and ask me about some of these things, and I will be happy to describe things. We are leading some of the work on vaccine design, as you notice, and we have 2 center grants, 2 U19 center grants from NIH for the vaccine design. And then we have grants for HIV treatment outcome prediction on how patients respond, and those patients that have heart disease and how they respond, and how do you design drugs. So, and of course we have, since I started out with cancer, we have lots of projects on cancer. Thank you. Any questions? Yes? Okay.
You can go ahead.
You go.
I have a question about the MRI images.
Yes.
Do you have an approach so far about how you're going to use those?
Well, the interesting part is that many of you probably noticed in the newspaper is that by the time you actually see the change in the image, it is too late for early disease diagnosis. So the reason why the neuropsychological data is really good is that I mentioned to you, it really takes only 5 to 10 minutes to do it. So when you go into physical, you can do it. And also this is quite important. And for those of you that are familiar with the traumatic brain injury because of IED, that's also a very good baseline for us to take measurements for all the military personnel. So we want very cheap and non-invasive measurements. Now, MRI is not invasive, it is not cheap, but also really a very minor change in MRI actually is caused by quite a bit of change already in the brain. So when you actually can see that. So it is a little bit too late from our point of view. But like I say, it's now imaging is advancing, and there could be a lot of advances in terms of nanoparticles do imaging that may be able to detect the minors, like the tiniest thing. But what we do, I think the neuropsychological data turned out to be really good. But we were given all sort of data, so we just use everything. But then what you notice is that you will identify the key one and the earliest one, right? So that's why those are important. Yes?
I don't know if you've gotten this question before, but when I see this, I think immediately of like p-values and ANOVA and statistics, and I don't think you mentioned statistics the word once. Do you intentionally?
I never use statistics, that's not my training,
Yeah.
right? Because right at the beginning, it is not p-test, that is very important. And p-test is a correlation. So remember the difference, and this is really about a decision-making process within the clinic, so it is very different.
Currently though, like, I'm sure there's, in the clinics or clinical trials, people, they normally use like logistic regression,
Yes.
things like that, and
Yes.
they put in like 1,000 parameters, and that's a problem. You're saying that's a big problem.
Yeah, there is a problem, and they realize that. I mean, in a sense that a lot, like it's mentioned to you, NIH and NLM, they realize that statistics are very important and integral in terms of clinical trials and study. So there's no question about that. But statistical approach, even if you ask really someone that is major in statistics and advancing the field, they know that there is a curse of dimensionality that is really difficult. Statistical approach are parametric a lot of times, so that's the really difficult part, because you notice, for example, in one of the study we have, very interesting, I have 13 individuals that behave in a certain way, and then 2 individuals that behave differently. So if you apply almost all statistical approach, it will classify everything into the first group. And it has very good results if you just look at one lump of accuracy, right? Without knowing, oh, you actually have 0 in the other group. So that's really the major difference. So I don't on purposely skip that, but I already noted that, right? Right at the beginning of my talk, I said the focus of this talk is not on statistics because I am not expert in statistics. But the good thing is that a lot of these problems that came to me have already read through by the statisticians. For example, some of the heart disease data, some of these has been analyzed by statisticians, and they were not able to come up with the patterns and also the rule itself. So that's the reason why.
Do you think then going forward for like, especially for students,
Mm-hmm.
I mean, I don't think there's enough statistical training for students, let alone these machine learning.
Yeah.
Do you think this is a really important field
Absolutely.
for students to get some experience?
Absolutely.
I
Yeah.
would love to.
It's like, I mean, for those of you that know artificial intelligence, I think that was really, really did thing like back in the 80s when that was before I was a PhD student, and then it kind of died. And part of the reason, it's kind of an interesting part, is that at that time it is difficult for them to validate things, right? You notice you have to be really bold to say, oh yes, now let's test the predictive rule. What if everything is wrong, right? So you will be like, all right, but you have to be brave. Sometimes, as a researcher, I really do like the what I do like to tell the students is that if you find out it works, that's great. We can write a paper. If we find out that it does not work, we still can write a paper so that others do not do the same thing and not knowing that it is not going to work. So I think being able to analyze it and being able to blind predict is really important. And the machines, the IBM machine that beat the human on the Jeopardy, a lot of them, that is actually very limited in a sense. It will have everything that remember and trying to connect everything, right? It's not yet the AI, but the true AI part is the Deep Blue, the chess machine, right? So why is it that it will beat the chess champion after 3 trials? If I were the chess champion, I will only play once. Why? Because as I'm playing, the machine is learning your steps, and the machine can move 1 million steps per second, right? So you have no chance but to be bitten, even if you are the champion. So that is the whole idea of machine learning. It's really powerful, but of course, those machines are designed just for playing chess. But if you look at these type of techniques, it is really, now AI, the reason why I mention AI is because it kind of died down in the 90s and the early 2000s. Now it came back in full bloom. So everyone is talking about. I think now people understand much better what's going on, and knowing how do you validate and be able to figure out what is right and what is wrong and sort things out. This is really important. If you can do studies using multiple clinical trials, that is really beautiful. And also if you can do studies, like for example, you have wet lab, and then you design a rule, you go back and have new studies and then check and validate, that is also very beautiful, because that gives you the ability to refine your rule, to validate, and to know what you find those patterns actually are important. Because I can tell you every single day there must be like millions of patterns, or if not billions of patterns that are being found, right? But at the end of the day, there may be just only 2 or 3 left, or maybe 0. I mean, I have on a regular basis, we find lots of patterns. And then as students always tell me, Dr. Lee, we have like, now we're running several trillion of that. I say, fine, continue to run, because I don't know where the validation goes, right? I'm not going to take the risk of like being sloppy in the analysis, because it is important. If you want to make it work in the clinical setting, that's important. And in the same way, like if you want to make it work in the consumer area, and like I said, those are getting very mature because it has a huge population base, right? We don't have that luxuries. And unfortunately, clinical trials really have at most maybe 100 patients. That's already a very big clinical trials. So that's why the statistical approach is very limited in that level. It's a very good question. Now, how do you learn this? You learn machine learning in the systems engineering department in the computer science. And then the biological side, you also learn how to integrate all the pieces together. That is important. So I hope I answered your question. But don't worry, like I say, everybody, all my students that started with me has no knowledge of this. I teach them on an individual basis, because I think sometimes there are things that they have to do it in order to know how to use the methods and advance it. Yes? Yes, I can. Sure. Yes. And I can also give you a book chapter that I have written that give you the detail on the challenges as well as like where to go. Like if you're a PhD student wanting to go into this area, then it lay out the issues that you should look at, because these are very hard problems. So it's not going to die. It's not going to go away. It's going to stay for a long time, maybe for another 100 years or so. We'll see. Any other questions? All right. Thank you. Like I say, if you have any questions, you can always email me. Thanks.